Hi, in this video we will calculate the values of the function sine and cosine and also the length of the perimeter of a circle numerically using a computer, using this software ifigures. Now, a computer usually already knows the value of these functions. For example, if I will write here sine of 3, it will give me some number. Now, this is sine where 3 is referenced in radians. So the computer already knows this. But how does it know this? How does the computer calculate the function? So it uses an algorithm. We are not going to necessarily do it in the same algorithm that the computer does. What we are going to try to do is do it with a very simple algorithm. So what we want is to be able to find the values of sine or cosine in radians for basically any number. So this can be done in many ways. We are going to do what I think is maybe the simplest way. So you do need to know something, some background math in order to follow this video. So first, you need to know what the sine and cosine functions are. We are not going to define them. You need to know about derivatives. You need to know that the derivative in radians of sine is a cosine and cosine is minus sine. And that's about it. So let's start. So what we want to do is for each angle A, and right here, let's say A, find the value of sine A. This is what we want to do. Sorry. Now, of course, the computer doesn't know what A is, and therefore it cannot calculate sine of A. But if we tell him A is, let's say, 0, then now he knows what A is, and now he can calculate the sine. And as you know, the sine of 0 is 0. But this the computer did. What we want to do is do it ourselves. So our answer, we will denote by a variable that we will call sine A. Okay, now this is a variable that the computer doesn't know what it is, because it's not any function, it's just a name. This will be the name for what we think the value is for sine A. Now, we can start with this particular case of A equals 0, and here we know that sine A actually equals 0. The way this will work is that what we will do is we will each time do a little increment in A, change A by a little bit, and then use the definition of a derivative. So if you change a variable by a little bit, then the change in the function can be calculated using the derivative. This is what we're going to do. And then we're going to do many of these small changes, increments. And what we will get is an approximate value for sine. It will not be exact. Any numerical calculation is approximate, but if we make the increment smaller, then we can get better and better approximations. So let's do that. So we need sine A at the beginning, but we also need the derivative. And the derivative is cosine. So we will actually do cosine and sine together. So our value for cosine is going to be denoted by the variable cosine A, which again, the computer has no idea what that is. Okay, it's a variable the computer doesn't know. And we know from simple geometry that for A equals 0, cosine A is actually 1. So now for this particular value, A equals 0, we know from simple geometry the values of sine A and cosine A. We don't need any numerical calculation for that. But now, as I said, in order to calculate these values for larger and larger angles, what we will need to do is choose a very small step in A. Let's call that dA. And let's say it's small. Small number is, let's say, 0.01. So now dA is a small number. Once we run this, then the computer now knows what is dA. Now, what are we going to do? Each small step, we will take A and first increase it by this amount, by this small amount. The way you do that is, the simplest way you do that is you write A and then you write plus equal, and then whatever it is you want to increment A by. Let's just try that. So each time I click here, you can see that the value of A grows by this small amount, 0.01. See? Okay. Of course, the computer doesn't know that sine A and cosine A are supposed to change because we didn't tell him that. He does know how to calculate using his built-in function for sine, the value of sine for any of these angles. What we need to do now is also tell the computer how to calculate the sine A and cosine A. And the idea is very simple. So if we changed A by a little bit, what we can now use is the definition of the derivative to change accordingly the value of the function. So for example, sine A is going to be increased also. By how much? So it's the increase in the function is the increase in the variable times the derivative of the function. Now we know the derivative of the function from the previous step. This is cosine A. So we just need to write here cosine A. And again, this is our numerically calculated cosine A, which here just started from simple geometry. So now we advanced sine. We also need, because during this calculation we will need cosine A, so we will also need to calculate cosine A in the same way. And cosine A is also going to change. So I will write it as an increase, and this is, again, the function increases each step by the amount that the variable changed times the derivative. Now, what is the derivative of cosine A? We know it's minus sine A. So let's put this in parentheses, minus sine A. Okay? Now each time, let's go back to the initial conditions where A is 0. And now each time we click this button, the angle changes, and so does our estimate for sine A and cosine A. And you can see already that what the computer thinks sine A should be and what our estimate is are very similar. They're not identical. This is an approximation after all, but they're very similar. Let's see if we can get to much larger values of A. Okay. You can see now we already got to 0.3 radians, and there is pretty good agreement between our numerical estimate and the actual value of sine A. So basically we achieved our goal. Now let's have some more fun with it. So first, let's have some graphical output for this numerical calculation. And the simple, intuitive, and nice thing to do is to put a point every time with the x and y at the cosine and sine. So what we are supposed to get is a circle going around. So let's do that. So we can just write point. And then if we put in the x value cosine A, and in the y value sine A, then we will just get a point. Okay, now you see the points are very, very close to each other because we're making very, very small changes. Just to see what happens that this is real, let's make bigger changes. Of course, our results will be more approximate. Okay, so let's go back to the beginning, make bigger changes, and now start over. Okay, now you can clearly see that we're getting points that are going around. Okay, and you can kind of notice that our values, numerical values for sine A, are less accurate than the ones we had before because we are making bigger steps and are accumulating a bigger error each time. Okay, now there is no reason we should do this manually. We can repeat this set of lines of codes needs to be repeated every time, and we can tell the computer to do that for us. So let's go back to the beginning. We can also automatically erase the screen by a command CLF, which is short for clear figure, and we need to add open parentheses and close parentheses. And each time this will clear the screen. We can also give it a better name. Let's call it initial conditions. And we can give this a better name, advance. Okay, the name doesn't matter, of course. And now, instead of just clicking here again and again, like I did before, what I can do is just call this. This is actually now a function called advance. I can just call it every 0.01 second or some other time interval I choose. Let's try this. So I can just write here advance. And now once I start to click it, let's do it slower, every 0.2 seconds, let's say, which is just repeat by itself every 0.2 seconds, it will run this thing. Okay. Now we can stop somewhere, let's say here. We got to an angle of 5.3 radians, and you can see our approximation is pretty good, even though we are using rather large steps. So now we basically did what we wanted. By the way, let's also check our cosine A. So this is our numerical estimate for cosine A. Let's see how good that is. So we can just calculate cosine of the same angle. You can see in cosine A there is a little bit bigger error. So let's use smaller jumps. Of course, now if we use smaller jumps and we still advance every 0.02 seconds, the advancement will be very slow. So there is no reason we have to advance so slow. We can also do this much faster. Okay. Let's try to stop at the same level of around, let's say, 5 radians. Okay, so now we're about the same value as we had before. Now you can see our estimate for cosine A is much better because we're using smaller steps. Okay, so now we can actually achieve another thing. So we know that by definition, the length of the curve in each step is equal. Since we are basically drawing a circle with radius 1, the length of the curve is actually equal to the amount of radians. This is by definition of the radian. There is no cheating here. So if we just go over and complete a full circle, we will actually measure the length of a circle, of the perimeter of a circle with radius equals to 1. And as you probably all know, this is by definition 2 times pi. So what we are actually doing here is calculating the value of pi. Let's try that. So let's continue to run this until we get closer to a full circle. Let's stop short a little bit, zoom in. And now we can do it a little bit more carefully and see when we are getting actually to a full complete circle. Okay, so let's zoom here. Let's say, I think we need one more. Now we're basically as close as we can to a complete circle without moving too far. This is the value we got. This is the length, approximate length of a full circle. And as you know, this is supposed to be 2 pi. Indeed, it is 2 pi. It's not exactly. If we want to see what 2 pi is, we can just write, the computer knows what pi is. It's called pi. This is really 2 pi, and this is very close. You can repeat this with smaller steps. Of course, you will get much better values. So in a few minutes, we were able to numerically calculate the value of sine, cosine, and find the value of pi. Thank you.